Hello everyone. In this video we're going to take a look at some of the practice problems that are identified at the end of the slides for this chapter. So you can see we have suggested practice problems 10.1 to 10.17, 10.29, 10.30, 10.32, 10.39, and 10.40. We're going to start right at the beginning and we're going to try out practice problem 10.1. This problem can be found in your textbook on page 353. This problem states that a 7-foot long auger is rotated 90 degrees to lie along the side of a grain cart, while the cart simultaneously moves 20 feet forward. There is an accompanying figure, and then it says to determine the displacement of point A at the outer end of the auger. So for a problem like this, it is helpful to redraw the figure, but we're going to do that in a 2D plane, so that makes a little bit more sense. So what we have is two positions. It says that there's a 7-foot auger and it's rotated 90 degrees to lie along the side of a grain cart. That means that it is actually starting fully out away from the cart and then is pulled in. So let's draw these two different positions. Okay, so here is a figure where we're showing two different positions. The one where the auger is fully extended, that is position 1. And then we have position 2, so the whole tractor has moved 20 feet and the auger now has retracted back inwards. So point A has moved along with, obviously, the whole tractor from point 1 to point 2. So all we really care about is the displacement of point A. So it has a starting position and it has an end position. So it's a little bit maybe difficult to understand what this looks like just because it's two moving components, right? A tractor going in one direction and then an auger moving another. All we really though care about is A, not the different bodies. We care about A. So A starts off, if we were to redraw this just so that we can see what's happening with A. If A starts at a point like this, we know that it clearly has to move inwards at 7 feet, right? It definitely moves inwards. And then it's also going to move downwards. So it moves inwards 7 feet, but it moves downwards. Now, the whole tractor moved 20 feet, but because the length of the arm is 7 feet, that means the total distance for A downwards would be 13 feet. And so therefore the displacement then from point A, from its original position to its final position would look like that. So if you remember correctly, displacement is a vector. So not only do we need a magnitude, we're going to need a direction. And so what we'll need to do is figure out some sort of the angle here, right? So let's draw that in as well. We want to find out what theta is in there. But we also want to know the displacement, and we're going to say that that's displacement, so the total displacement for A. Or if you want, instead of being confused with the point A, we can even just call that S for displacement. And so S, since this is a right angle triangle and we have two sides, we can use the Pythagorean theorem. So S is equal to the square root of 13 squared plus 7 squared. S is then equal to 14.8 feet. As I said, that's not the final answer because we need the angle as well. If we then say that tan theta, remember tan is the opposite, so that would be 13 over adjacent, which would be 7. then we would find that theta is equal to 61.7 degrees. And so what I like to do then, when we're writing out our final answer, we can just say that the final displacement is 14.8 feet. And we know that that's at an angle of 61.7 degrees relative to the horizontal when we draw it that way. Okay, so that is the answer to 10.1. Okay, let's try another one. Let's take a look now at 10.2, also on page 353. Here it says that a forklift truck lifts a pallet 2 meters off the floor and then moves 7 feet ahead and sets the pallet on a stack 1.5 meter high. We want to determine the displacement of the pallet and the distance it traveled. So both displacement and distance. So again, we're going to start off by drawing where it starts. We know that we can call that maybe O for origin. That's where it's starting. From there, it moves up. We said 2 meters off the ground, so 2 meters. We then said that it moves ahead 7 meters, so we'll go across 7 meters. And then it says that it sets the pallet on a stack 1.5 meter high. So if it's 1.5 meter high, that really means then it's just going down 0.5 meters. Okay, so we want to know what the total distance and displacement is. So distance would be easy because that is just the addition of all of those movements. So the distance is equal to 2 meters plus 7 meters plus 0.5 meters, which is equal to 9.5 meters. And it's just a magnitude since this is a scalar, not a vector. For displacement, remember that's the difference between original position to final position. So it's helpful then to draw out that vector. We know that it should look like that. So we want to figure out what S is, and we want an angle relative to the horizontal. So if I extend out a line here, then that would be that value there. What is it relative to the horizontal? And you might say, okay, well, that's not within the geometry shown. That's okay, though, because if I were to draw out another line parallel to that first line that I drew, then I know that due to the Z law, that these two theta values are the same. And so that helps because now I can use the geometry to my advantage to figure out what the theta on the inside is, and then I know what that is on the outside. So therefore, displacement, we'll call that S, is equal to, well, we have that inside triangle, right, where we have 7 on the one side, 7 squared, plus, this is where you'd be wrong if you said 2 meters, because the triangle that we care about here would just be this triangle right there, right? That's the triangle that we care about. So it's 7 squared plus 1.5 squared. And so S is equal to 7.16 meters. As I said, we need to figure out what theta is. Okay, so again, we just use tan theta is equal to opposite, which is 1.5, over adjacent, which is 7 meters. So we can find that theta is equal to 12.1 degrees. Therefore, S is equal to 7.16 at an angle of 12.1 degrees. And as always, try to either highlight or put a big red box around your final solution. Do another one here. Let's take a look at 10.7. So we'll go to 10-7. And so this one will be found on page 354. It says that a stunt driver travels a total distance of 1,172 feet, moving at a constant speed of 40 miles per hour while weaving through an obstacle course. If the total displacement of the car is 600 feet from the start of the course to the finish, determine the car's average velocity. So all we want to do here, we want to determine the car's average velocity. So it sounds simple enough. First thing I like to do is if you either draw it out or you write out at least all of the knowns. We are given the fact that distance traveled here is 1,172 feet. We're also given that the displacement S is 600 feet, didn't give a direction. And we are given that speed, so remember speed is not velocity, it is just a scalar, so there's no direction with speed, and that's 40 miles per hour. And one thing I want you to see right away when you are writing down all of your knowns in a given problem is you want to look for the units, make sure all the units are consistent. So we have feet, and then miles per hour. So miles and feet do not align. We want everything in base units. That would actually be feet per second in a problem like this. So we're going to have to convert this miles per hour. So we're going to say that that is 40, we'll write that out, miles over hours. So if we have hours on bottom, we need to get rid of that by multiplying it by hours on top. We know that there are 60 minutes per hour, but we want this in seconds. So we'll have to multiply that by minutes, and we know that there are 60 seconds in a minute. So we're going to have to divide by 60 twice. Next, we want to get rid of hours. So an hour on bottom, we need an hour on top. And we would now need to know what that ratio is. How many, not hours. Did that again. So what we're going to need is we want to get rid of miles. So definitely need miles it's on the bottom since the 40 miles per hour is on the top there, those miles. So we need to know the ratio here. For every mile, how many feet are there? So this is something you would have to look up. It is in the textbook. And it's 5,280 feet per mile. And now if you take out all of the units here, you'll see that we should be left with now feet per second. So we take 40 and we need to multiply it by 5,280, divide it by 60, divide it by 60. And we get 58.7 feet per second. Being in Canada, we often will deal with both SI and US customary units, so we have to be able to convert between the two, or just even within one of them, go to base units like we're doing here. Okay, so we have speed involved here, we have distance, we have displacement. What we need is an average velocity. Remember, we're given speed but not velocity. We have displacement, we have distance, so a bit confusing as what we need to do. So if you're ever unsure, then write out the equations that we would be using in a case like this. So for velocity, we do know velocity is delta S over delta T. What we can then get from here, and it may not be completely obvious, is the fact that we do have speed, which is a scalar, and we have distance, which is also a scalar. So we can actually figure out the time from that, where delta t is equal to 1,172 feet, and we're going to divide that by 58.7 feet per second. And you know you're going to be left with a time just by looking at the units. That's why it's so important to write out your units. If you divide feet by feet per second, we're left with units of just seconds. And you can do that in this case because we're given two scalars, and those two scalars will help us determine the time. So that would be a total of 20 seconds. Now, of course, we can use that based on the displacement that's given. So therefore, V is equal to 600 feet for the displacement, and we're going to divide that by 20 seconds. And so then that gives us 30 feet per second is our velocity. Okay, the last problem we're going to look at for this section is 10.8, and that is shown on page 354. In this problem, it states that an object travels from the origin to point 1 in 5 seconds, then point 2 in a total time of 8 seconds for a final displacement of 5 feet, as shown in the figure. Determine the velocity from point 1 to 2. So I'm going to start by redrawing this figure. Okay, we're tasked to find the velocity from 1 to 2. So from point 1 to point 2, based on what's given. Again, we start at an origin, goes to point 1, then to point 2 with a final displacement of 5 feet. And so let's write out the equation for velocity. We know that v is equal to delta s over delta t. So the one that we're looking for here is S2. S2 is our delta S here. And we're going from T2 minus T1. Where we do know, might as well write out what we know, delta T is then equal to 8 minus 5 seconds. So that's just equal to 3 seconds. So we need to solve for S. Okay, we need to solve for, for S2 out of here. Now, it may not be absolutely clear when you're looking at this figure, but I did draw out the angles. So we see that we have 75 degrees above that horizontal line, and it's 10 degrees below that. It almost looks like that 10 degrees in the bottom right corner, but it is not. It is basically saying that that entire angle is 85 degrees. So if that's the case, if you remember, there was a particular equation that we could use to solve for a side of a triangle that is not a right angle triangle, where we have its opposite angle, but we don't have any other angles, as long as we also have the other two sides. And that is the cosine law. So that is written as follows. We're going to take S2, square it, and we're then going to add the sum of the squares of the two sides that we do know. So that would be 6 squared plus 5 squared. And then we're going to subtract 2 times those two sides, 6 times 5, times the cosine of that opposite angle. So that is 85 degrees. So S2 is equal to 7.5 feet. So we know that that is the displacement for S2. We don't have an angle though, and that will be important because the velocity will be acting at the same angle here. So we know that it's at some angle like this relative to the horizontal. So I'll choose a different color here. What we want to do then is figure out what the angle is right in there beside that theta. So the only way to get that angle, that outside angle, again, this is where you might have to be a bit creative. If we were to draw out, if we were to extend that horizontal line between the 75 and the 10 degrees, let's extend that out. Now we're breaking this up into two different triangles. In fact, that line that I extended would be parallel with the line that we have at the top. That also means then that that internal angle there, so we'll give it a name then. We're going to say maybe that's beta. So those two angles are the same. We have 75 degrees on the inside angle on the left-hand side. So what we would have to do to get to beta is potentially find theta first. Now that we have all the sides of the much larger triangle, we can then use the sine law to determine what that angle theta is. So let's do that. We can then say that 5 feet over sine theta, remember, as opposite lengths to the angle, so sine theta is equal to S2 that we just found, which is 7.5 feet, to its opposite angle, which is sine 85 degrees. So from there, we rearrange and we solve for theta, and you will find that theta is equal to 41.6 degrees. Now that we have theta, we know that beta is equal to 180, because a full triangle is 180 degrees. So it's 180 minus 41.6 minus 75 degrees. And that gives us 63.4 degrees. So that is this angle right there for S2. It's important because that will tell us what the angle is for velocity. And velocity is a vector, and it will follow the same angle that we get for displacement. Okay, so therefore velocity is equal to 7.5 feet. We're going to divide that by our time, which we said was 3 seconds. And that's equal to 2.49 feet per second at an angle of 63.4 degrees. And there is our final answer for velocity.